So in 2008, we've done all this work in sulfur, and I went to a forensic meeting and I met a bunch of police forces and people that were telling me about how hair had some valuable information and they didn't know how to get it out of it. And it just clicked in my brain. It's like, why can we not do sulfur and carbon and all these things in hair with a laser? Oh, you're crazy, you're never going to get it, you know, it's impossible. And it's like, yeah, but your hair grows as you eat and as you travel, so surely all these things go into your hair. And when you pull somebody's hair out and analyze it in the lab, it must tell you something about their whereabouts and what they've been doing. Oh, I don't know, you never get money for that. So we did get some money for a feasibility study. So I nearly ended up bald. This is not real, this is real. No, we used loads of hair at the beginning because so the problem with hair is that it's a biological tissue, so it burns really quickly with the laser. So we had to do a few trials, went back to police forces, got them to give us a bit of money to try the methodology. They were really excited about the fact that hair is just hair just falls out. They don't have to ask anyone for permission. They have to ask permission to get a DNA sample. But if a suspect goes on a train in central London, when he leaves that seat, chances are he would have left some hair behind. That hair can then come to the lab and we can do some analysis. So there was no methodology whatsoever. We had to optimize the parameters for the laser ablation conditions. And then we had to see if the sensitivity was good enough for us to see any sulfur that comes from the keratin in the hair. So we did get some signal, and with some tweaking of the conditions, we did get to the point where we had a methodology where we could look at one single hair strand, as opposed to having to digest a bunch of hair strands pulled out of somebody's hair. We could now look at one single hair strand at a time and tell the sulfur isotopic composition of that hair strand, and then work it backwards to changes in that person's basically diet or geographical location. That we were not sure what kind of information this was going to give you. So the problem in this case, we've got hair from A and B, so yes, obviously I'm B, and my colleague here is A, both living in the UK for a pretty long time, and then we have a friend, C, a traveller, that has been lucky enough to travel around the world and lived in each one of these places, so Australia, Croatia, Austria, and then the UK for more than a month. So that was the ideal candidate for us. So I went to this girl and smiled and was really nice to her. Can you give me a bit of your hair? You know, slowly we were friends. So she had to give me her hair. So she gave me a lot of her hair, and we started doing tests with our hair. And are we going to be able to tell the difference? So the answer is yes. We proved the concept. Not only we had a method that allowed us to look at one hair at a time and measure the sulfur isotopic composition and have an uncertainty associated to it and be comparable to gas source isolation mass spectrometry, but we could now see the 4.5 centimeters of my hair and the other guy, A, were pretty boring and dull, and they didn't have any changes in isotopic composition because your diet is pretty much the same. Whereas these individuals that had been traveling around the world and had been to 4 countries so far had massive changes in their hair. At this point, I couldn't tell you if this was Australia or this was Croatia. You know, we don't really know, but we know that the first few centimeters are the new ones, and she had been in the UK for the past 2 months. So this was stable, and then the changes. So we had proved the concept and published this a couple of years ago. So just to give you a bit of information of what's happened since then, because I'm not going to finish this story and then move to the next one, and then you'll be like, what's happening with the hair then? So we've also looked at carbon ratios. We've now started a pilot study with police forces in the UK, and we've collected hair from 120 individuals, and they've basically given us hair and their consent to look at isotope ratios. And we can see that in terms of carbon, there is an isotopic signature for these people that have not traveled around that much. And there's also some changes for the people that have been traveling. So chances are that the combination of sulfur and carbon isotope ratios in hair are going to tell us something about where people go. This is really interesting for police forces, where they could be examining evidence or hair samples from 3 suspects, and one of them could have claimed that's been in the UK for a really long time, when in fact they've been traveling over the world, you know, learning how to explode bombs or fly planes. And this is just the worst case scenario. You could also use these for diet and basically nutritional studies as well. this is as far as we got. And obviously my question was, when we looked at this data for sulfur, for carbon, this is done by ICP-MS. So could we maybe use the laser and the ICP-MS to do carbon as well? So then once again, I went back to the lab. You're crazy, you never get to do carbon by laser ablation ICP-MS, you never get it on the multiple lecture. Conventionally, it's been done by ICP-MS, which means again that the sample has to be combusted to CO2, and then you still need an oxygen correction, and you measure in 44, 45, and 46. You're not really looking at 12, 13 ratios. So with all those problems and the associated uncertainty that comes with, we had to look for an alternative where we could look at 12, 13 ratios. So this was me, and that was a challenge. So we know that ICP-MS has really poor ionization for carbon. This has been, written in books, and we know that what goes through the plasma, less than 5% of that is what you will see as a signal. Added to the problem, carbon-13 is only 100 times smaller than carbon-12. So you have a great signal if you do for carbon-12, and then a very small one if you do for carbon-13. So I went back to the literature, and there were only a couple of papers at the time that were published for carbon ratios, trying to use an ICP-MS. One of them was a home-built twin ICP-MS, and the other one was just a paper where they looked at the carbon isotopic dilution. So not much in there in terms of guidance for me to start the experiment. So we just started tweaking things in the ICP-MS again, and we did see some carbon, we did see some carbon-12, and we did see some carbon-13. So ask me how this happened. It just happened one day that I was reading fire, and I thought I was dreaming, and then I went back, and it works again. And I think the trick was to use the ultrasonic nebulizer and get rid of any potential interferences that could come from C12 and 13. And we did see this. The background was fairly small, again, against all odds. And we then had a method where we could measure carbon-12 and carbon-13 ratios. So we went on to validate this method, what we had at the time, which were the NIST standards that, again, geochemists and cosmochemists use for their studies, which is certified for a relative number, so a difference between two standards, which again we don't really like, because we like isotope ratios and we like absolute numbers, but this is what we had. So we converted the numbers in the certificate to the absolute ratio, and we plotted against what we were getting with the new methodologies. And you can see that it works pretty well. It is linear, and it covers the whole range. So our method would be useful to look at compounds that vary within this scale. So we published this a year or two ago, and we then had a new method that had been validated with the 4 NIST materials that were available at the time, from -50 to +40 per mil, which is the expected scale of variation for organic compounds. Once again, we had to use a pair of isotopes of similar mass to correct for the mass bias. So we tried boron 11 and boron 10, and that worked for the mass bias correction, as is shown in the graph. We calculated the uncertainty so that we could compare to existing methodologies, and we proved that we had a new method that could look at all those compounds of interest. Expanding uncertainties are less than 0.05%, which is really good and compares really well with RMS technology. What's more interesting about this methodology is the fact that you are getting 12-13 ratios rather than delta values. So if I gave you a sample and you were to do the same analysis in your lab, regardless of what standard you used or what correction you used, we should all get the same number, rather than me having to tell you exactly how I've done mine, so that then you can replicate to get the same number. So we then thought about this method and what are we going to do with it. The possibilities are endless because it's nothing done. There are no standards for this kind of methodology. Carbon ratios is something that hasn't been touched because they thought they had what they needed, so why do it anymore? And there are quite a few fields out there, forensics and sports testing, that need standards for these kind of measurements. So we talked to WADA, the World Anti-Doping Agency, and the National Measurement Institute in Australia. And they had a problem. I don't know if you know this man here. So at the time, the way they do the analysis is they measure the testosterone epi-testosterone ratio. And where it's more than 4, that's taken as a positive case. The case is taken further, and then they do some more analysis. This really is not, I mean, this is what this guy was fighting the whole time. The fact that the methodology on itself wasn't that great. It wasn't validated, it depended on ethnics, it depended on body weight, etc., etc. So he was fighting for a long time until they did some RMS analysis, and they really discovered that testosterone didn't belong to his body. So if he was to take it from the outside, the carbon isotope ratio would be different than if it was his own testosterone produced endogenously in his body. For these kind of measurements, surprisingly enough, they still use geochemical standards. So how can you be measuring testosterone ratios in a urine sample against a rock? Really, there's nothing to do one standard with another. So regardless of the methodology and how well you think it works, it hasn't been validated with the right standards. So what we propose is to look at some progesterone and testosterone and characterize those for isotope ratios, and then use them as the right standards and be able to produce an isotope ratio rather than a delta value. So we have been doing some work on this, and we recently published JAAS. And this paper was basically just an opener to the endless number of applications that this methodology could have. Something we could do in-house, because at LGC we also have a purity laboratory and a reference material produced in laboratory. So we could purify some progesterone in-house, we could then look at it and characterize it isotopically, and because we also have conventional RMS technology, we could compare the values. We then sent the samples to our friends in NMIA and WADA, and guess what? The numbers match. So this standard could be characterized with both delta, so that we keep the geochemistry stable, and isotope ratios, so that any biological or police forces that were to do this analysis could have a number and an uncertainty attached to it. So this is as far as I got from my time at LGC. I hope I've convinced you that multi-molecular ICP-MS has really met initial expectations, at least for me. It has done everything it was supposed to do and more. It still has a drawback in the sense that there are some cases where we need matrix separation, and that's a bit of a problem, and added a term of discussion. But in my case, for stable isotope ratios, it really has done everything I was expecting and more. It's still very much a geochemical and cosmochemical tool, and it's making its way up to the analytical community. More than 40 elements have now been done from leaking to uranium, and we now have added carbon to the list. So where do I think that things are going? I thought I'll give you a hint of what I would like to see happening within the next few years. To me, the coupling of HPLC to the multi-molecular ICP-MS to be able to have compound-specific carbon ratios is a must, and that's something I started before I left LGC, and I hope this work carries on. To look at amino acids and be able to tag amino acids and give them an isotope ratio value rather than a delta value would open endless possibilities for archaeological samples, nutritional studies, etc. Once again, we also need standards for this kind of analysis, so to me the method development should come with production of standards. And in terms of forensics, we've looked at hair. We should try this with laser, and then we'll be able to tell the same as we've done with sulfur for carbon. We should also try this with nails and bones, and also of archaeological and forensic evidence. I think we could do a lot for the forensic community and industry. We could produce standards associated to this methodology. So I told you about the future of multi-molecular ICP-MS. This is my future. It's the Institute of Photonic Sciences in Barcelona, and I invite you all to come and visit, not at the same time, because my flat is really small, but come and visit. It's a really nice place. It's a photonics institute. We do anything to do with light and photonics and lasers and photovoltaics technology, optoelectronic devices, etc., etc. So I'll be happy to talk to you about it later on. And I just want to thank everyone in here who has made it possible for me to be here today. My past employer, LGC, in the UK, stands for the Laboratory of the Government Chemist, now LGC. It's in Teddington in the UK, and one of you has been there for a few months. Wei Chao, you're there. And Tsinghua University for having us here today. Thank you so much. Such a great opportunity for me to be here. These four guys here, the usual suspects. Unfortunately, one of them is not here today, but you recognize the other smiley faces, and I invite you to go and talk to them and get your research published in JAAS, because it really is not just a journal, it's a bunch of friends, and every time you see them you realize how lucky you are to publish there and to get to know these people. And obviously my new boss at ICPO, the Institute of Photonic Sciences, that has allowed me to be here today, and you for listening.